Morning all. So today's job is a good customer of mine. He has an Audi A4 with a 2-litre diesel TDI engine, 2012, and the symptoms he was experiencing are a rough idle, occasional power loss, and the car cutting out. It's an intermittent problem. Sometimes you can go a period of a few weeks without having any issues at all, but more recently it's become more frequent, and he asked me to look into it. I've already done a bit of diagnostic testing. Important to say that there's no warning lights or engine lights up, but I'd like to take you along on this one because I actually think it's quite interesting. The way modern diesels now, it's a fuel supply related issue. On this particular system, it's a Bosch. It's one of the latest Bosch systems. I think it's EDC 17. There have a few generations of those. The EDC 15 was in a load of cars a few years back, 16, and this is I believe, one of the newest incarnations. And what I think is particularly interesting here is how the computer has a lot more control over fuel pressure regulation. And the reason they do this, Volkswagen program and invest all this R&D into having more accurate and more precise control over fuel, is one, emissions control. Obviously European standards dictate that cars need to be more fuel efficient, be burning less, creating less toxic emissions. And secondly, it's for economical reasons. If you have more control over fuel at any given load or engine speed, then you can prevent wastage of mechanical energy by a pump. Effectively, the high pressure pump has a very limited range of pressure that it can create. It's a rotary mechanical system, but what the developers of this engine management system have done, have created 2 points of control. One is a metering valve into the pump itself, sort of like a throttle, which changes the amount of fuel from the low pressure side of the system entering into the pumping chambers of the high pressure pump. And the second is at the end of the common rail, the rail which holds fuel pressure and dampens pump vibrations. The second is what's called a DRV. It's a back pressure regulating valve, and this can leach off pressure from the common rail if it sees excessively high pressures. And again, this dual point control provides a much more economical fueling. So I'll get you on the scan tool once I've finished the test drive. Important to notice, I've taken the car for a test drive to get a feel for it. It's a dynamic thing. You can gauge with experience parts that might be an issue just by a test drive. You know, if you had a faulty fuel pump, as I said before, it's a mechanical issue. Once an element of it, a pumping chamber, is worn or it's not sealing right, you're going to have a problem all of the time. It's not going to resolve itself. Given the symptoms that the customer is describing, I'm moving less away from that and more towards the pressure controls on that fuel supply. So here's the customer complaints. We have the engine is what I would describe as hunting. It's not a regular idle speed. As I showed you, it has a fuel pressure fault code. I have the lab scope set up on the signal output of the high pressure sensor on the fuel rail, and I have my other lead on the duty cycle control ground line of the inlet metering valve on the pump. And as I described to you, that valve is what throttles the amount of fuel that actually enters the pump from the low pressure side of the system. It's actually important to note that the customer did get the fuel filter changed in an effort to sort this problem out. It didn't make any difference. As you can see here on, and get a good, the yellow trace here is fuel pressure. You can see those fluctuations. You should have at idle speed maybe a steady 1 volt or so. It's quite erratic, and as a result of that, the inlet metering valve wavelengths are actually changing. You shouldn't see too much change in the on time, in the ground time of this when it's idling, but it's obviously seeing the fluctuations in rail pressure, and it's trying to compensate by allowing more fuel into the pump. If I stick a trigger on this, just to trace 2, we want the trigger on, just to keep it steady. You can see the degree of on time is changing all the time, so we have an issue with fuel pressure regulation. The next test is going to be to disconnect this inlet metering valve, which will open the valve completely up. It will log a fault code, but what that will do is it will allow complete flow from the pump to the rail, and then I'm going to ground out the DRV, the valve on the rail, which actually returns fuel back, and see if the system is capable of generating full pump voltage. What I'm hoping to see is the fuel pressure, this yellow trace, peak between 3 and 4 volts and hold. If it doesn't hold, then we need to investigate what is actually causing the pressure to be released from the system. Okay, so I've changed my setup. I'm now on the pulsed ground of this DRV. The waveform, I've changed the time base because the event that's going to happen is going to happen very, very quick. What I'm going to do is I'm going to ground this out, which is going to close the valve completely, and so long as that is grounded, the system should hold full rail pressure, and from that we can analyze degradation of the fuel pressure by looking at this yellow trace here. So I'm going to do that now. I have a jumper wire attached to ground. What is going to happen is the computer in the car is going to recognize that there is a fault, and it's actually going to switch the car off, the engine off, very, very quickly, and that's why I've changed my time base to a 5 millisecond for this case. So I'm going to ground out the pulse width control wire for the DRV to ground. We're going to watch the yellow trace, which is again, it's fuel pressure. I've disconnected the inlet metering valve, which is essentially causing it to open fully, allowing full flow of fuel into the pump and therefore into the rail, and I'm going to ground that out. The car is going to stop because it recognises a critical fault, so that's why I've actually changed the time base to 5 milliseconds, and then we're going to watch the yellow trace. What we hope to see on a good functioning system, that's generating full pump pressure between 3 and 4, maybe 4.5 volts, to determine whether this pump is A, capable of generating pressure, and B, whether there is an issue with the integrity of the fuel system itself. So I'm going to ground that out now. Okay, so fuel pressure is at 2 volts, dropping. You see that yellow line falling down, down, down. this system is not holding pressure. I'm going to take it off now. You can actually hear the valve clicking open and dumping all that fuel into the return system. So we have a system that is not capable of holding maximum pressure, a very, very quick degradation or decay in fuel pressure in the line, and we now need to investigate why that is the case. What do we know? We know that the inlet metering valve is being actuated, is being pulsed in coordination with the fuel pressure signal. Do we know that this fuel pressure sensor is 100%? No, we don't, but look at the symptoms. A car that drives very, very, very well, except it has a bad idle. For me, this sort of rules out an issue with the pump. As I said, it is a mechanical system. If it was bad, if there was an issue with sealing within the pump chambers, I'd expect not only a rake of fault codes, but also just poor performance throughout engine load and speed. I can't 100% rule it out. The injectors themselves, which are underneath this piece of sound deadening material, they are the piezo type injectors. Again, the self-diagnostic function of the system itself, if it does recognize any issues, usually will flag a fault code. They become hydraulically sealed without current, as they are in this situation now. I believe if there was any issues with a leaking injector, we would have fault codes for those. Bear in mind, we only have the single one for fuel pressure regulation. My feeling is that it is actually within this back pressure valve, and this is what I'm going to attack now. I believe what is happening is the valve is sticking, which would correspond with the symptoms that the customer is having of an intermittent bad idle and poor performance, and as a result of that, the valve isn't shutting completely, and it is actually letting pressure out of the rail. So this is what I'm going to actually replace based on that logic. So the valve is fitted to the common rail. The common rail is fitted back to the engine. All the high pressure pipe work has been reconnected, the sensors, and now in order to prime the fuel pump, we need to actuate the electric fuel pump. We use this program here. Where are we now? Electric fuel pump relay. We'll start that up. I'm not sure if you can hear it in the back there. The fuel pump is cycling. Do that a few times. We will also cycle the auxiliary pump, which is auxiliary fuel pump. That's the one which is underneath the car next to the fuel filter. We'll start that. Oh, that's a lot louder. You can hear that. We'll cycle that a few times. Okay. So that's priming the fuel pump, as I say. Dip the clutch, start her up. And the first thing that's noticeable is that we have no hunting, which we had before, this sort of surging effect. I'm going to redo the tests, but in the meantime I'm just going to keep an eye on the... In fact, no, what I'm going to do is I'm going to set the scope up again, let this reach operating temperature, and we'll redo our tests and see if there's any difference in the fuel pressure readings and the decay. Now bear in mind that we will probably have to go through a relearn procedure in order for this idle to completely smooth out. So bear with me in that regard.